Thanks, Mike, for that great introduction. It's a pleasure to be here. I do a lot of reviews for the journal, and it's nice to see the faces with some of the names that I read so much, and the great reviews that many of you turn in. It's really a pleasure. So I'm going to tell you today a little bit about statistical problems in preclinical research. My talk has another title that I think it'll be easy to remember. It's this one. So it's a bit loaded of a topic there. So I don't have any disclosures with the industry to report, but I do have a couple of NIH grants that I'm working on. Okay, so in 2005, John Ioannidis published an article that had this as a title. And it was the shot heard round the world. At the time, I'm not certain I was ready to believe it. Most studies are false. And of course, we'd have to define what false means, and I'll take a shot at that later on. But I'm not sure what you think about it, but it certainly has started the era of thinking that science is in crisis. As David did a great job of explaining to us, we're having trouble replicating even our most basic work. We can't replicate it out of our own laboratories, and we're having trouble doing it certainly in others. So let me see if I can paint first for you the evidence that we are in fact living in a crisis where most research findings are false. So People's Exhibit A is the replication crisis, now has its own Wikipedia page. If something has a Wikipedia page, it must be true, right? So there it is. I think this table is really kind of a nice comment on human nature. The left column, or the middle column, this was a survey published in Nature on scientists from these various fields in the rows trying to replicate others' work. 90% of chemists said they had trouble replicating the work of others. And then on the right column is trying to replicate their own work. So most scientists thought there was a problem in replicating others' work, less so in their own. But I think that could be because of methodology variance. You're doing the same thing over and over again. But I also think it points to the fact that this seems like a problem that others have that perhaps I don't. And so my talk today, one of the goals is to try to convince you that this is a problem we all have. And I'll show you some of the techniques that maybe bring it to our doorstep. So the replication crisis has been very popularized by failing to replicate others' work using a p-value. One group found a result to be statistically significant, another group did not. But another common problem, this would be Exhibit B, is the disappearing effect size. Well, it turns out this problem has been known for a long time. Rhine in 1930 first described it. Kronbach in 1975 described it as generalizations decay. The first laboratory that finds an effect size, that would be the one on the left, finds a very strong effect size. And then future laboratories, not only do they fail to find the same effect size, but the more you study the topic, the more it seems to regress to zero. There's a great article in the New Yorker called "The Truth Wears Off." If you want to get a nice colloquial version of that, it's right there. So the disappearing effect size is something we're also dealing with. And Exhibit C is the dog that didn't bark. Most prediction models are never replicated or used in any way. Quick literature search found 56,000 prediction models reported or published from 1978 to 2016. Of these, 346 had a replication study or were used in the literature. Most of the things we're doing are finding results that describe our data really well and appear to be exciting, but that others fail to find so. And I think this is a big problem in replication studies. So there's my three exhibits that what we're dealing with is a serious problem, both in terms of replicating others' research, replicating our own work, and seeing effect sizes that then disappear. So what I'll do is I'll tell you a little bit about the causes of the crisis in a very limited, focused way. They're very multifaceted, and I think anyone who's thought about this topic knows that there's many, many reasons that we'll have trouble replicating work. The rate of publication is much higher than it's ever been in human history. There's a pressure to publish. We have to find interesting, innovative things. The worship of novelty. The most novel the findings are, the more likely they are to get in published journals. And of course, innovation is also probably associated with a low prior probability of being true. The reason why something is exciting and innovative is because we haven't seen it before. And if we haven't seen it before, it could be because we just haven't looked hard enough, or it could be because it's not true. The other ones are fraud, which our field has really had to deal with. We have, of the top 10 fraudsters in academic history, 3 of them belong to our group, to our anesthesia community. And then, of course, p-hacking, researcher degrees of freedom, and selective publication. I'm going to combine a couple of these into something called the Garden of Forking Paths. It's a new metaphor that I hope you like. It's pretty easy to remember, and I'm going to walk you through it. And it's a way to think about researcher degrees of freedom in analysis. So let's get started with that. So if you were to have a how-to manual on a statistical test, it might look something like this. Straight out of 1950. It's a brand new t-test. Look how happy they are. Why wouldn't they be happy? They've got a brand new t-test to use. Well, if we were to look on page 1 of this manual, of any parametric statistical test, it would state, the data must be a random representation from the population being studied. Now, I say that, and we can all agree, but this is where the problems begin. The data have to be a random draw from the population. It can't be the same data analyzed 100 times, or, as I'll start to show, looking inside that data many, many times, then also starts to make those data less of a representation of the population of which they were drawn. Okay, and then a corollary of that is that the observed data must represent only one realization of a process that could be indefinitely repeated. So we could draw another sample using the exact same methods and observe another test statistic, maybe a t-test. And what we'd see is we'd see variation around this test statistic. But that variation should be well described by our measurement error. This is what inferential statistics is. We combine all sources of error into something we're going to call measurement error, and we know it pretty well, and we can plan on it for future studies. So why isn't that working here? Why are we living in a time where measurement error and our confidence intervals are not working? Well, that's what we're going to talk about. So I'm going to go back to Gelman's approach for this, and get used to this table. I'm going to bore you with it over the next 10 minutes. I'm going to show you several different versions of it. But Andrew Gelman, who's a statistician at Columbia, has come up with the metaphor, the Garden of Forking Paths. And he'll illustrate it for us using these 4 test cases. And I'm going to walk you through all 4. So some of this isn't clear. I'll show you some examples of it. But there's a couple things we need to know off the bat. We've got the middle column there. We have Y, which is the test data. So we've randomly sampled a population in our preclinical research. We've got observed data. That's Y. The other parameter we have there is something called phi. And all phi is here is on the bottom row there, if you can see the note. It's simply analytical choices. Things we could have done, things we could condition the data on, choices we could make on analyzing these data. They could be control variables, covariates. We could transform the data, log transform them. We could do different data coding rules. We could do exclusions, outliers, main effects, interactions, subgroups, alternate outcomes, or, ready for this, we could even change what we think the direction of the effect is. We expected one group to be larger than the other, but in fact one group was smaller than the other, and we can interpret that as being what we had planned all along. So phi are choices we can make along the way. So as you see, phi will play a different role in each one of these situations. So let me get started. So here's my garden. I've created for you a garden that's only a 2x2, but in practice, the garden is really a hypercube. There, you saw a lot of different choices I can make, a lot of different ways to analyze these data. This is really many, many dimensions, but I'm going to reduce it to 2 just for our conversation today. On the x-axis is phi 1. So let me just say this could be outlier removal. So we've collected some data, and on phi 1 are 6 different choices I can make in outlier removal. Phi 2 is artificial dichotomization. I'm making this up. It could be anything. But I'm going to cut the data into artificially dichotomized versions, and I could do 6 different ways I could do that. So together, I've created 36 different possible combinations of how these data, which were a random representation from the sample, from the population, could have been analyzed. In our first case, which is a classic t-test, I only analyze one of them. I don't make any choices. As the data were pulled down, I run my test statistic, which is a t-test in this case, and that particular case is what I find. Let me just say one more thing, which I failed to mention. What I have here is in the 6x6 matrix, there's different intensity of colors, and they're green, because this is a garden. There's a garden of forking paths, so of course these are green. But what I have here is just in this particular thing is random effect sizes represented by a z statistic. It could be any difference here, but this is z, meaning the greater the z, the more the effect size. And this is what this data could have shown. The one I'm going to report to the world is down in that lower left-hand corner. But I could have, had I made different choices, reported several different of these. So I'll show you why that might look in a second. But in a typical t-test that's classically the way Fisher would have done this back in 1930 would be this one here. Okay, the next case I'm going to show you will hopefully highlight the problems with the garden of forking paths, and that's number 4, fishing. Fishing, of course, is a pejorative term for looking at all possible combinations of my data and artificially selecting the highest one. What I'm going to do here is I'm going to do a test statistic, which is conditional on the data, that's y, but it's also conditional on my phi, on the choices I make in the analysis. So let me go back to the data set. Here's my forking paths again, and now I'm going to literally test every version of these. I'm going to run a t-test for every combination of these. And look at that. I found the one that has the highest effect size, and I'm going to get tenure. This is the one I would report to the reader. I'd fail to report any of the others because they're not as interesting as this one, and this is the one I report to everybody. This is clearly a bastardization of null hypothesis testing. I don't think many people do this. I think fishing is something that we all know not to do. That being said, if anyone's doing it, don't. It's a bad idea. This is multiplicity. And this is what we're doing here is we're doing extreme score selection. With all the choices we could have made in this data, we're taking the most extreme score, the most extreme effect size, and that's the one we're pulling out, and that's the one we're going to tell the world about. Okay, a different version of this could be number 2. In this particular one, what we're doing is we're doing pre-chosen set of phi. So this is what's really popular in clinical trials right now, where you're going to do a study, so you're going to pull a random sample down, but you're going to pre-register all of the choices you're going to make. So I'm going to do exclusion criteria, I'm going to do a transformation, I'm going to do a bunch of different things to the data, but I'm going to tell you about them ahead of time. As a matter of fact, I'm even going to publish these before I look at the data. And then when I analyze the data, I'm going to execute this as written there. I don't get to make any other additional choices. If there's a new outlier that I didn't think about, if there's a new fee that I could have decided but I didn't, it's got to be in the analysis as planned. And that would look something like this. I made, in this particular case, I just said I choose option 1 for fee 1, option 2 for fee 2, and it's right there. What's also popular in clinical trials is I can do multiple. So I can say, well, I'm going to make a couple different. I'm going to look at an interaction. I'm also going to look at a subgroup, maybe males versus females. All that's appropriate if you pre-specify and you make adjustments for multiple comparisons. Of note is that these effect sizes will be pretty close to the effect sizes we would observe again. Okay, the last one I'm going to tell you about is the one that is the major problem, and this is the one I think that is nearly ubiquitous in preclinical research and one that isn't on most of our minds. It's test based on the data. So what you see here is you have a test statistic based on Y, but the fees are also based on Y. So the choices I make in my analysis are conditional on the data. Now that doesn't mean I'm running hundreds of tests. Far be it. I can only run one test, but I would have ran a different test had I had different data. I would have made different choices had I had different data. And here's the garden of forking path metaphor. I start off and I look at the data, and all of a sudden I realize that, wait a second, maybe I could remove some outliers. Then maybe I could dichotomize a variable. At each point along the way, I'm moving towards a higher effect size. We don't know how analysts make these decisions. So one of the things I think is pretty ironic about modern applied statistical analysis is we know a lot about how the tests work, but we don't know a lot about how they're actually used in practice. I'd like to put a keylogger on some of my young analysts' computers and watch them make quick decisions in real time on how they're going to analyze the data. And what you see here is that by doing the garden of forking paths, you're walking through the garden of effect sizes that you could have observed, and you're going to report one that is more extreme than had you not observed that data. I hope that's clear. And if I ran the study again when I try to replicate it, what I would see is that the effect size is probably not going to be as large as the one I'd found, because I had implicitly tuned my data, my analysis into the effects that I observed. I only ran one test. There's not a multiplicity argument formally, but implicitly it's absolutely there. Okay, so we have our 4 situations. Let's see what happens with replication. If you only run one t-test and you do the initial study and you replicate it, you'll observe within sampling error about the same rate. You won't observe the problem of the diminishing effect size. If you do the pre-registration, exact same thing. If you do the garden of forking paths, you're likely to find a larger effect size. Why? Because that's what you were doing. You were honing in on conditional on your analysis to either reduce error variance or increase effect size, probably both. But when you try to replicate the study, and other people do another random draw from the population, what you will discover is that your study found an extreme score, not the actual representation. It wasn't a random sample from the population. And fishing, of course, is even more of that. You took the most extreme score you could find on that given day. You report to the world, and when you try to replicate it again, what you discover is that it will regress greatly. And so what you see here is part of the replication crisis. So let me just summarize, and if you're going to remember one thing about the talk, here it is. I think we all know that phishing is bad, and I don't think we're doing it. I think we all think we're doing a pre-chosen analysis plan, and then we're analyzing our data according to a preset hypothesis. But I think in reality, many of us are doing this. And at the risk of sounding preachy, I'm going to stop here and tell you I do this. I've been a part of analyses where we thought we were doing this. But when we look back at the track of the code, what really happened was that we were slowly snaking our way through higher effect sizes, lower error variation. This is something that is very easy to do. And the only way to avoid it is to completely pre-specify your analytical plan. Write the code to analyze the data before you even look at the data. And everything else looks like this. Okay, so then let me just circle back and tell you a little bit more about what then we could mean about being false. So typically we talk about errors in analyses. We talk about type 1 and type 2 errors. I'm not going to go into that. I think we all know what those are. But Gelman tells us there are really 2 different types of errors we should be focusing on. Type M and type S. A type M error is the one we've been talking about. It's the error in the magnitude of the effect size. Because if you do phishing and you conduct all possible tests in a data set, and the effect size is large enough, you could still reach statistical significance. It's going to be harder, but you could still do it. But your effect size is still going to be extreme. And when you try to replicate the study, it's going to regress back to the population average, which is probably less than what you observed. So type M errors are when we start to see the magnitude of the effect decrease, usually towards the mean or towards 0. Type S errors are the most egregious, and we actually deal with those more than we'd like to. That's where you get the sign of the effect size wrong. Not only is the effect size you're reporting to the world not the right magnitude, it's also the wrong direction. And why you can get into that is if you use the garden of forking paths, you look at some interaction terms, et cetera, you could really trick yourself into thinking that, well, what I've got here is a true effect, but in actuality, it's an opposite effect size. So type M, type S errors are probably a lot more important for our current crisis than type 1 and type 2. All right, so what's the recipe for greater chances of a study being false? Here it is, and it's a lot of stuff that David told us about. Small effect sizes are more likely to lead to the garden of forking paths because you have to go in there and start taking a look. You start to try to condition your data. Small or modest sample sizes, large measurement errors, and of course high variation. And another one, of course, is a low prior probability of effect. If the thing you're studying has a lower chance of being true, it's going to take a lot more data, a lot more likelihood to make the posterior chance of it being true. And I don't think in science we deal with that enough. Right, so I took a shot at trying to guess what I thought were the top 3 forking paths that investigators use. The first one I think is the one that's the most common. It's one reasonable scientific hypothesis can map onto many statistical hypotheses. So you hypothesize something and you think you've done it clearly, you think you've got an atomic hypothesis, but in actuality, that could actually play onto a lot of different statistical tests. Like for example, yeah, I think that PONV is associated with age, but really women are more robust to aging than men, so I should look at the interaction term. I didn't think about that ahead of time, but I'm going to do it now, and sure enough, there it is. So that's a great way to forking path in your way into kidding yourself into thinking your effect sizes are more robust. Second one's interaction moderation. And then the last one is controlling for confounders. If you didn't think something was going to be a problem, like for example, you're running your preclinical study and you're recording several different variables, well, you could always control for an additional variable during analysis. And that will tighten up some of the error in a lot of cases, and then you'll find a stronger effect size than maybe you would again. So I think those are the top three. All right, let me begin by closing up by trying to guess what some possible reactions you could have to this. Scientists can probably be placed into two broad categories on the left and the right. Those who are more deductive and those who are more inductive. I think the main action is right here. Should science proceed from carefully crafted inferences, or do you think this is true? The very idea of science is to learn from your data. You have to explore your data to learn what it tells you. If I just collected the data and I analyzed them in one way and then just pushed the data aside, I haven't learned what I could have from that data set. And therefore, I'm wasting money. I'm being inefficient on my resources. Most good scientists that I work with think that's true. I think that's true. But the problem is that the tools we use for evaluating truth in these data sets aren't built for that. And I think that's the real problem we have, and I think that's one of the major issues we have in the garden of forking paths in the replication crisis. So I think this is a great conversation to have with your statisticians, or if you're doing the data yourself. Certainly in the analysis shop that I'm running, we grapple with this on a daily basis. And it's really hard to overcome. All right, so here's some recommendations to close on. This is an easy one. Avoid the garden of forking paths. Pre-registration. Do fixed statistical plans. Actually have your analysts, or if you're doing it yourself, code the analysis before you see the data. Doesn't mean you can't explore the data later on, but the analysis you did ahead of time will be the one that is the most robust to regression to the mean. There's some really great coding software out there now. For example, R Open Science, the statistical package R, has Open Science, and they actually have a lot of great tools for this. All right, if you're in that second camp and you're more of an inductionist, I think if you want to continue to do it, then you have to be aware of a couple things. Okay, one, the p-values from your analyses are suspect. The confidence intervals that you've calculated are too narrow. If you come up with a test statistic and you've got confidence around it, and you've done anything other than a pre-specified hypothesis, then your true confidence intervals are going to be a lot wider than you've observed. And how much wider? Well, it's going to be wider proportional to the amount of forking paths that you used. And because those are implicit and difficult to count, it's going to be difficult to know. And then your effect sizes on further study are going to regress to zero. You need to be aware of that. So then when you report this, I think you need to describe the true plan of your analysis. See if you can attempt to describe to the readers all the degrees of freedom you took in doing the analysis, and then see if you can discuss the issue in the discussion. These are some small things you could do to help with the community. One thing I think is interesting is inductive inference. If you're going to play with your data, you could use Bayesian statistics. I like to say that Bayesian statistics is inductive inference for adults. Don't pretend that the p-values and everything is working very well if you apply them inductively. They're not going to work. But Bayesian statistics actually has a formal rule set for this. The data in Bayesian statistics are not assumed to be random. The data are assumed to be fixed. It's the parameters from those data that are assumed to be random, and you can play with that. And of course, allow others to reproduce your work and try some internal replication. So my final slide is, most published research findings are false, but a little replication goes a long way. So one of the best ways to protect yourself is internal validation of your own data, actually running replication studies in your own laboratory, bundling those together with the actual manuscript and the publication. It'll actually show how robust your findings are to these threats that I've been talking about. Thank you very much.